Okay. Good evening to all. My name is Dinesh. I am going to give a short lecture on Kaplan turbine. So before going into what is Kaplan turbine, we need to learn what is a turbine. A turbine is nothing but is a work producing device. It is used to generate electricity. So therefore we are calling it work producing device. This Kaplan turbine is nothing but is an axial, reactional and axial reaction turbine. Why we call it axial is pretty simple, because it is parallel to the axis of rotation. If you see in this diagram, uh, the flow comes and enters the runner vanes in an angle parallel to the axis of the rotation. Therefore, we call this an axial turbine. And you may ask me why we call this a reaction turbine. So the simple answer is here, since the pressure drop is happening across the runner vanes without the presence of any externally simulating devices such as nozzles or orifices, discharge probes, etc. So since we are using only the runner vanes, we call it a reaction turbine. So here we have an axial reaction turbine. So how does it work? This is the question you can ask me. So if you see here, this is the scroll casing. This is the scroll casing is there. If you see it from the top, you will get this image. This is the top view, this is the front view. In this thing, if you see means in the scroll casing, it will have a decreasing circular cross-sectional area. It will be like the diameter will tend to decrease. And as this decrease facilitates the movement of water into the runner vanes in a more constant velocity, and this constant velocity helps to avoid the swirl effects. Swirl in the sense, if you have a whirl effect, you will generally have more pressure on the blades and there will be more damages. To avoid that, that is why we are using a decreasing cross-sectional scroll. And then we have the guide vanes. Guide vanes are nothing but they turn the fluid in a 90-degree angle to align it with the axis of rotation, so that we are able to generate much speed. So now if we see this diagram, as the water enters the guide vanes and then enters the runner vanes, this is the runner vane. Water will have to attack the runner vane at an optimum angle of attack. If you generally see, say let this be a blade, the velocity, absolute velocity is at an axial direction, v1, and the peripheral velocity u1 is at a tangential direction, and then the relative velocity omega 1 is at an inclination. This inclined angle of attack should be optimum. So here I call it as alpha 1. So if this angle is optimum, we will be able to create a perfect rotation using this, and through this rotation of the shaft, we'll be able to rotate the generator shaft and we'll be able to generate power. This is the final objective. When the velocity hits the blade and moves over the blade has an aerofoil cross section like this. Therefore, it will have a lift, and the tangential velocity of this lift causes the rotation. So that is a point which we have to remember. And second thing, why we call this as a Kaplan turbine? There are two kinds of turbines, Kaplan turbine or propeller turbine. When the runner vanes can pitch themselves, pitch in the sense, if a blade is inclined at an angle of 20 degrees, and if it can change it to itself to an angle of say 5 degrees or so, then we can say it is a pitching effect. If a runner vane can pitch itself or change its angle, then we call it a Kaplan turbine. If it cannot change its angle, it's called a propeller turbine. So we have to understand this point very clearly. And one more thing which I want to mention here is, in this diagram, if you see means once the water is passing through the runner and it comes through the draft tube and it discharges out, the flow generally won't be fixed. In any condition of the year, we can never say that uniform flow is not possible. So when the flow changes, the runner vanes can be, first, if the flows tend to be higher, they tend to be aligned in a more vertical direction. If the flow tends to be lower, they tend to be aligned at a more tangential direction. So that is something which we have to remember. And one more application of these Kaplan turbines is that the Kaplan turbine itself is now used in many dam projects across India. For example, if you take the Polavaram project in Andhra Pradesh, they are using 12 Kaplan turbines, each of 80 megawatt capacity. So totally 960 megawatts of pure hydroelectric renewable clean energy is able to we can achieve through Kaplan turbines. Now one more question you'll ask me, like what kind of dams you are using Kaplan turbines? In Kaplan turbines are majorly used when axial, reactional, low head and high flow rates. Low head in the sense if you see many ground or earthen dams, heads are going to be less than 40 meters or something. It will be less than over 80 feet or 78 feet. But the reservoir size will be pretty big. For those kind of circumstances, with high flow rates, we can apply a Kaplan turbine. So these are the major distinctions about major things which I want to say about the Kaplan turbine. Now we will go for the velocity triangles of a Kaplan turbine, and we will find the work, efficiency, and then design procedure. Okay, so when we go for the velocity triangles, so say let the velocity entering the vanes be V1 at an angle of alpha to the horizontal. So this component V1 with alpha 1 is nothing but VW1, or it is the whirl component. And now we will find the peripheral velocity, which will be actually less than this, which is nothing but U. And the line joining this is the relative velocity. V1 U R. Or say we'll say it is VR1. So this angle is alpha, this is beta 1. So if you see, say